We can start. Good evening to all of you. Today in this session, we are going to discuss about signals and systems for the GATE exam. In the session 1, we are going to introduce basics of signals and systems. This particular signals and system subject is an easy subject if you practice a lot of problems and as well as questions from this particular subject. You need to prepare thoroughly the fundamental concepts and as well as the topics which I am going to deal in the first 2 sessions. Then you can build the confidence and you can attempt it easily. You need to practice well so that you may score full marks from this subject in the GATE exam. From the syllabus, we can observe that the syllabus consists of the basic understanding of the subject and the topic, a particular topic called digital filter design techniques is introduced in the year 2016, which you can observe, and it is there for 2021 GATE exam. So due weightage is given for this particular digital filter design technique. Convolution is again an important topic that we are going to discuss. Then we will have discrete Fourier transform, Z transform, Laplace transforms. So all these important topics we are going to deal. The preparation strategy should be like you need to follow the standard textbooks, standard materials. The best books you can identify signals and systems by Oppenheim, and for particularly for digital filter design technique, you can find the good concepts and as well as topics from John G. Provoke's textbook. So these are the best books, and standard materials also you can follow. So this is a brief introduction about the syllabus and how the preparation strategy should be there for your subject. So you have to thoroughly prepare regarding these topics. So as far as the outline of this particular session is concerned, we have to first introduce the signals, then we'll discuss about the classification of signals, then we will discuss about the classification of systems, then various signal operations we will discuss, and also we will discuss some of the GATE previous question papers in this particular session. So as far as the weightage of marks given in the GATE papers, if we do the analysis of weightage given in the previous GATE question papers, you can observe that in the year 2020, 10 marks. So on an average, you will find that there is about 10.5 marks weightage is given. And as we discussed earlier, if we prepare well, we can score full marks from this particular subject. So the introduction to signals. So how do we introduce a signal? A signal is a function of one or more independent variables that convey the information to represent a physical phenomena. So it consists of one or more independent variable, whereas the function itself is a dependent variable. For a function f, if you observe f of t1, t2 and so on up to tn, each of tk is an independent variable, while the function value is a dependent variable. And if we consider various examples for the signals, a voltage signal in an electronic circuit or a current signal in an electronic circuit. Similarly, position, velocity, and acceleration of an object. And if you consider a mechanical system, the force or torque. And if we go for a chemical process, the flow rate of a liquid or a gas. And in image processing and video processing applications, you can see a digital image, digital video, or digital audio. All these comes under signal processing. So now let us try to understand the classification of signals. So here we are talking about the classification of signals based on various criteria. The first criteria being how many number of independent variables are there. Based on that, one classification. Based on the number of independent, whether the independent variables are continuous or discrete. Based on that criteria, again another classification. Based on the dependent variable, the next classification comes. And we are going to distinguish between an analog signal and a digital signal. Most of the students will get confused and will not be able to properly define what is an analog signal and what is a digital signal. We are going to discuss that. The first criteria being based on the number of independent variable. A signal with one independent variable is said to be a one-dimensional, a single dimensional. For example, an audio signal. A signal with more than one independent variable is said to be a multi-dimensional. The example being image, which we have discussed earlier. And now, another criteria based on the independent variables. The independent variable may be continuous independent or discrete independent. So a signal with continuous independent variable is said to be a continuous time signal. And a signal with a discrete independent variable is said to be a discrete time. Now, this is based on continuous time and discrete time. Now, the next classification comes based on the value. So, a signal with a continuous dependent variable is said to be continuous valued. And a signal with a discrete dependent variable. Observe, earlier with independent variable, we said it is a continuous time. Whereas we are now talking about a continuous dependent variable and a discrete dependent variable. So based on which you can say it's a discrete valued signal. So a continuous valued, continuous time signal. So if both value is continuous and as well as time is continuous, you can say that signal as an analog signal. A discrete valued, discrete time signal is said to be a digital signal. A discrete valued, discrete time signal is said to be a digital signal. So we can observe the variation between the difference between an analog signal and a digital signal. So what is the difference? You can find easily. Analog signal is a continuous valued and as well as continuous time signal, whereas a digital signal is a discrete valued as well as discrete in time. Hence, it is said to be a digital signal. Now, let us take an example of continuous time signal and discrete time signal. So here you observe that the signal is continuous in time, whereas the right hand side signal is a discrete time signal, which is discrete in nature at different time intervals. You have the amplitudes, you do not have any continuous amplitude here, and also time is discrete in nature here, in discrete time signal here. And now let us define a system. Often we say our subject itself is signals and system. We will say often about system. So let us define what is a system. A system is an entity which processes one or more input signals in order to produce one or more output signals. So the system will process the input signals in order to give us the output. The outputs may be one or more. So here we have clearly defined what is a system. So let us move on to classification of systems. Here again, different criteria are taken for classification of systems. One is based on the number of inputs, another one is based on the number of outputs, and the types of signals the system is going to process. So based on these criteria, we will classify the systems. So based on the number of inputs, we say a system with one input is said to be a single input. A system with more than one input is said to be a multi-input. And based on criteria of number of outputs, a system with one output is called single output. A system with more than one input is said to be a multi-output. So, for example, if you take a radar system in a practical case, so you may have a multi input and multi output systems, multiple inputs and multiple output system, which is shortly called as MIMO system, that we can observe in the case of radars. So radar communication will make use of that such kind of multiple inputs and multiple output systems. Now, based on the types of signals that are processed, a system can be classified in terms of the types of signals that it processes. And also, consequently, the terms such as the following can also be used to describe the systems that we already discussed, the types of signals, and here the types of systems. So, one-dimensional system, or multi-dimensional system, and based on these continuous time systems and discrete time system, analog system, digital system. So, for example, a continuous time system process continuous time signals, and a discrete time system will process the discrete time signals. So we'll pictorially or with a block diagram, we'll see what the discrete time system will do and what a continuous time system will do. If you take a discrete time system, so it will process discrete time signals only. So but if your input is a continuous time signal, so what is to be done? So you have to convert your continuous time signal into a discrete time signal by making use of a converter. So hence you will find the first block as conversion of a continuous time signal to a discrete time signal converter and give it to a discrete time system. Then the discrete time system will process your discrete time signal, and then it will give you again a discrete time system. But at the output side, what is to be done is I want a continuous time signal as my output. So you need to convert your discrete time signal again into a continuous time signal. So hence you can see the processing of a continuous time signal by making use of a discrete time system. So as we are processing with discrete time system, you have to convert your signal, continuous time signal, into a discrete time signal, then process in a discrete time system. Then again convert your discrete signal into a continuous time signal making use of a converter. Now, when it comes to a continuous time system, and in case if your signal is a discrete one, then we are going to do this process. Convert your discrete to a continuous time converter, making use of a discrete to continuous time converter. Then apply that as an input for your continuous time system. Then after that, whatever you will get a continuous time signal, then convert it into a continuous to discrete time converter, making use of a converter. So here, this block diagram is for processing a discrete time signal with a continuous time system. So we are very clear that our input is, here we are saying it is a discrete time signal. As the system is suitable for processing a continuous time system, we are converting it. So that's it. So this is a simple signal processing system that you can understand. How do we process? And a best practical example that we see is that this where do we use these signals and system? Everywhere in communication system. Suppose we have a message signal that is transmitted, making use of a transmitter, and the transmitter signal will pass through a channel, and at the receiving end we will receive the signal, and we will get an estimate of the transmitted message signal here. So this is just a general structure of a communication system. So far we discussed about various kinds of systems, and let us move on to the different operations that are used on the signal. So these operations are very, very important for us in solving the number of problems, whether based on convolution or filtering techniques. So whatever the signal processing operations you take, so these properties plays these operations plays a major role. So by knowing these operations, it becomes very easy for us to do the analysis. So hence we will discuss different operations like time shifting, amplitude shifting, amplitude scaling, time reversal, and as well as amplitude reversal. The first operation on the signal being time shifting, we will discuss about time shifting operation. So what is time shifting? The name itself will suggest that it is the shifting of a signal in time. So how do we do this shifting process? This is done by adding or subtracting the required amount of shift to the time variable in the function. And we have taken a particular case when t greater than or equal to 0, subtracting a fixed amount of time from the time variable will shift the signal to the right, and hence that becomes a delayed signal. So do remember, this is the case when t greater than or equal to 0. But when you take t less than or equal to 0, the subtracting will will result in the shift of the signal to the left and advance by an amount. So the reverse will happen when t less than or equal to 0. So do remember this condition we have to check thoroughly when we are doing the time shifting operation. So while adding to the time variable will shift the signal to the left, that is advanced. Let us try to understand this with a simple example. So the condition here, we are taken a continuous time signal x of t, and time t1 is greater than 0. Now you replace the time t in x of t with t minus t1. Then what happens? The x of t signal becomes x of t minus t1 as we replace t with t minus t1. So as that is a delayed signal. So you observe the delayed signal x of t minus t1. Here the amount of T1 is taken as 1. So you observe that there is a right shift here. And as well as here, the time when replacing t with t plus t1 gives you an advanced signal x of t plus t1. Here you observe that x of t plus 1. So you have the time shift operation here clearly. So now let us try to understand more about time shifting operation by taking various problems and various examples we will discuss. So suppose x of t is the input signal, given signal, and y of t is a time shifted signal. Y of t is equal to x of t plus k, and you are given this particular x of t signal, for which here the amplitude is indicated as 1, and it is going to start at origin with t is equal to 0, and the upper limit where it is ending here is 2. So for this, if you are asked about find x of t plus k, so for example, you take an example. So as we discussed, the amount of time shift, whether it is less than 0 or greater than 0, is more and more important here for us. So when let us take the y of t is equal to x of t plus k greater than 0 case, and k is equal to 2. Let us take this particular example. And if you take this example, y of t is equal to x of t plus 2. So this is the case of a left shift. So this is your original x of t signal, which is shifted to the left with here you observe that minus 2. So this is a case of left shift. And now take the other case, second case, when k is less than 0, and in that case our y of t is x of t minus 2, as k is replaced with minus 2. So you observe this is a case of right shifting. So we have both left shifting and as well as right shifting based on the value of the amount of shift, based on the value of k, whether it is greater than 0 or whether it is less than 0. So we have taken an example and we discussed the case of left shifting and right shifting. So the next important property that we are going to see is amplitude shifting. So you observe here a waveform with an amplitude of 2, and y of t is your amplitude shifted signal, and x of t is an input signal, and we want to shift that x of t signal by an amount of b, where b is a real number. So here, geometrically amplitude shifting adds a vertical displacement of x. So we have taken the value of b as the value of b may be a negative value or a positive value. If the value of b is a negative value, like in this case, the value is being -2, then the downward shift, because the amplitude is uh, below the x-axis and a negative amplitude value. So here you observe that the shift happens, the amplitude shifts, the vertical displacement on the y-axis, either above the amplitude value or below the amplitude value. This is what will happen. What is the meaning of vertical displacement of x? And let us take another case here. X of t is our input signal, and y of t is equal to x of t plus k. And x of t signal is given by here the x of t. How do we define x of t? And for all values of t less than 0, that is on the left hand side, for all negative values of t, do we have any amplitude of x of t signal? No. You can clearly observe that there is no amplitude, and x of t is defined simply as 0 for all t less than 0, whereas the amplitude is 1 in between 0 and 2, and hence we can write x of t as 1, 0 less than t less than 2. Now for this particular case, you are asked to find out what is the value of uh, -1 plus x of t, which is y of t. Y of t is equal to -1 plus x of t. And you can observe that there are three different conditions. When the value of t less than 0, you observe that the x of t value is 0, because on the for the negative values of t, there is no x of t signal, that is, it is 0. So we substituted 0 here. And for the case of t lies between 0 and 2, we have clearly the amplitude of x of t is 1, and we substituted here 1. So -1 plus 1, it is 0. And for all the values of, similarly, for all the values of t greater than 2, you have x of t amplitude as 0. So we got these values for three different conditions. So with this, we will be able to draw an amplitude shifted signal in an easy manner. Like -1, it is -1 for t less than 0, it is 0 for in between 0 to 2, and it is -1 for t greater than 2. And hence you can observe here, yet t less than 0, that is on the negative x-axis side, you can observe that we had given an amplitude of -1. On the y-axis, it is indicated as -1, and it is 0 for in between 0 to 2. So it is on the x-axis itself, as the amplitude is 0. And for t greater than 2, we have an amplitude of -1. And now let us take this case when k, so far we discussed about when k less than 0. Now take the case when k greater than 0. When k greater than 0 means that is +1 plus x of t. So x of t is 0 again for t less than 0, and x of t is equal to 1 for in between 0 to 2, as just now we discussed, and x of t is equal to 0 again for all the values of t greater than 2, and hence we got the values are 1 for all values of t less than 0, x of t, y of t, y of t is equal to 2 for 0 less than or equal to t less than or equal to 2, and then it is 1 for y of t is equal to 1 for t greater than 2. Now let us plot y of t, which is 1 plus x of t. So it is the case of upward shifting. So you can see the shift of this amplitude, and hence it is the case of an upward shifting. And now let us take another simple operation on the amplitude. It is called amplitude scaling. The scaled signal, x of t is your original signal, and ax of t is the scaled signal. Say suppose 2x of t, that means your x of t is multiplied by a constant of 2. or by a constant of a. So what happens? Here the amplitude is 1, and as it is multiplied by a scaling factor or a constant of 2, so you got here the amplitude as 2. So the upper one is the case of a continuous time signal, and whereas this is a discrete signal. Wherever you will find x of n, you can understand that as a discrete signal, and it is scaled by a factor of a, and hence you are going to get a discrete time signal scaled by a factor of 2. You can observe here. And time scaling, this is again a very important property of your signal, as the name suggests that t is scaled by a factor a. Here let us take that the x of t signal got scaled by a factor of a. So time scaling maps the input signal x to the output signal y, as given by y of t is equal to x of at, where you can observe that a is a non-zero real number. So such transformation is associated with dilations, with dilation and or time reversal. So you can have two cases again here. What are the two cases here? You can observe that the two cases are being, one is the scaling factor for which modulus was taken, that is greater than 1, and another one is if mod a greater than 1, the signal is compressed along the time axis by a factor of mod a. And if mod a is less than 1, that is scaling factor is less than 1, the signal is expanded along the time axis by a factor of 1 by mod a. And we will better understand this time scaling property by means of an example, and a plot or a graphical representation will give you a good idea about time scaling. So let us go for it. Before going to that, if mod a is equal to 1, the signal is neither expanded nor compressed. We may get a doubt. We have defined mod a less than 1 and as well as mod a greater than 1. Now the question comes, when a is equal to 1, what happens to the time scaling property is that the signal is neither expanded nor compressed. If a less than 0, the signal is also reversed. That is also called as a time reversal property. This is a special case of time scaling. For example, x of t is there. What about x of minus t? How do you get x of minus t? Is you are multiplying t with a negative value, minus is scaled by a factor of -1. Hence, you are getting a time reversal signal. So, and the time compression or expansion is a special case of time scaling with a greater than 0. So we can better understand the time scaling property by making use of a simple example. Let us take a plot of x of t in which the signal is having some amplitude, and it is getting extended between -1 and +1. And on the right hand side, extreme right hand side on the topmost, you observe that there is a waveform in which x of 2t. So this is the signal, the time, it is time scaled by a factor of 2. X of t is time scaled by a factor of 2. And you observe what is the value of 2, it is greater than the time scaling factor mod a is greater than 1. Hence, the signal is compressed along the time axis. So what is meant by compression? In the previous case of x of t, you observe that the time axis is between -1 and +1. If mod a is greater than 1, the signal is compressed along the time axis by a factor of mod a. That means you observe here, you got -1 divided by 2, which is -0.5, and -1 divided by 2 here, again plus 0.5. So you got a compressed signal. If mod a less than 1, the signal is expanded or it is stretched along the time axis by a factor of 1 by mod a. So you observe the stretching of this. So often one may get the doubt, like if I multiply the time factor by a scaling factor, why it is getting compressed. So I'm not comfortable with this concept. So for that case, just we can simply understand this concept by taking a simple example, a numerical example. Let us take y of t is equal to x of 10t. That means the x of t signal is time scaled by a factor of 10, and now substitute t is equal to 0. Then what happens? Y of 0 is equal to x of 0, and t of substitute t is equal to 1, and so on. You go on computing till your y of 5, which becomes x of 50. And if you plot these graphs of x of t and as well as y of t, you observe x of t here at it is on the time scale 10, 20, 30, and so on here, whereas y of t is here. So by the time you observe that y of t goes to 5, x of t takes the values at t is equal to 50. So hence you observe that whenever a is greater than 1, it is the case of compression. So we are going to get a compressed signal. So this is how you can understand very easily in time scaling property. When a greater than 1, it is the case of a compression. And again, let us take another example here. So here we have the two cases, when a greater than 1 and when a less than 1. We plotted this one. And let us generalize and simplify this particular time scaling property so that we can quickly do the problem, especially useful in objective type questions. When there is a limited time, you can straight away apply this general rule and you can get a time scaled signal in a very easy manner. Let us try to understand. Here x of t signal is given for us, and we are asked for x of 80 where a is greater than 1, x of 4t, 4 is definitely greater than 1. So here you observe that the lower limit got divided by a factor 1, and here again the upper limit got divided by a factor a. So here, if this is the case, so a is a generalized scaling factor. Now here in place of a we have 4. So in the lower limit you just divide your lower time limit value, which is 0, by 4, and upper limit, which is 2, by a value 4, again by a scaling factor a. So you got 0 and 0.5. Now let's take again another example. So this is a simple triangular kind of waveform, and you are asked to find out x of t is this plot. You are asked to find x of minus 3t, x of minus 3t. So how do I find is just we will do a simple exercise here. Let us take t dash is equal to minus 3t, and it lies between minus 3 less than or equal to less than minus 3 less than or equal to minus 3t less than or equal to 6. Now we need to find this t value. So how do we find, as this is minus 3t, how do we get 3 is divide this limit by minus 3 and as well as divide this limit again by minus 3. So we are going to get here 1 plus 1 and here as minus 2. So the signal x of minus 3t signal lies between minus 2 and as well as plus 1, and hence this is a easy way of solving for time scaling. So if a is less than 0, the signal is reversed. So this is the case of time reversal, as just we discussed. If a is equal to minus 1, so x of t is there, x of minus t is nothing but a time reversed signal. So the time reversal is a special case of time scaling in which the signal folding will take place around y-axis. So you observe, so here what is given? You are given x of t and you are asked to plot x of minus t. What is x of minus t? Is a time reversed signal. So how do I get the new time axis after doing the time reversal or time scaling? Is here again the same what we did earlier. Minus 1 less than or equal to minus t less than or equal to 2. and we need to divide it again by a factor of minus 1, and as well as here. So you get plus 1 as one limit, other limit is being minus 2. So minus 2. So you get here the limit as, so you just take this x of t signal, and along the y-axis you fold your x of t, and you observe that you are able to get the time reversal signal, which is x of minus t. That is what the meaning of folding a signal along the y-axis. So the time reversal case here. And there is again another operation which is called amplitude reversal. In this case, signal folding will take place about x-axis, whereas you observe here in the time reversal case, the folding is taking place around y-axis, whereas in the amplitude reversal you observe that the folding is taking place about y-axis. So you take x of t and minus x of t. So here the amplitude reversal is taking place, and you observe that your minus x of t signal lies below the x-axis. So here the folding we did about the x-axis. So this is how we can understand the amplitude reversal. Now, in most of the gate exams, you can find not a simple one single operation. You may find multiple operations on the signal, like time scaling combined with time shifting, both time scaling, time shifting, time reversal operation. So to cover all these kinds of operation, let us take a simple question, and you may try to solve this particular signal. X of t is given for us, and we are asked to find x of minus t, that is a. B is x of t plus 2, and C is x of 2t plus 2, and D is x of 1 minus 3t. So if we clearly observe the first one, x of minus t, what is this particular operation? Just now we discussed it is a time reversal operation. So because in the time scaling, it is a special case. If a is minus 1, it is multiplied with minus 1. So you got the time reversal. And x of t plus 2, again, it is the case of a time shifting operation. And now the third one, that is C, which is x of 2t plus 2. What are the operations involved in this particular problem? If you identify, try to identify what are the operations. One operation is time scaling, that is t multiplied with a factor of 2, and hence we get 2t. It is a time scaling. Again, 2t plus 2, it is again a time shifting property. So we got both time scaling and as well as time shifting. And now you take the fourth case, 1 minus 3t, and you better that you understand there are three operations got involved in this particular question. There are three operations that got involved in this particular question. You can understand that. So the first question, you can observe the x of minus t need to be done. X of minus t is to be done. So how do we do x of minus t? Is the mirror image. You observe this is the mirror image. This is the mirror image. X of minus t signal is the mirror image of x of t, and hence we can understand x of minus t can be easily computed by taking the mirror image of x of t. So amplitude remains the same, Also the reversal occurs about t is equal to 0. Now let us take the other case. So the other case B, where we are asked to find x of t plus 2, x of t plus 2, and hence what is to be done is we have to first get x of t, and then it is time shifted by a factor of t is equal to minus 2. So hence you get a left shift here. This is a shift in time at t is equal to minus 2. The vertical portion occurs. So you observe that this is a easy case of time shift. And now comes the third case, where you are asked to find x of 2t plus 2. Again, if you remember, let t dash is equal to 2t plus 2. By quickly adopting that tip or trick, one can easily find that t lies between minus 1 and 1 by 2. That can be done. Just please work out this one. So 2t plus 2 less than or equal to 3, 0 less than or equal to 2t plus 2 less than or equal to 3. If you work out, you will get minus 1 less than or equal to t less than or equal to half. On the extreme right hand side, you can observe that there is a plotted signal, okay, with the time limits as minus 1 and 1 by 2. Again, you have an x of t signal on the left hand side, and you are asked to find x of 1 minus 3t, x of 1 minus 3t. So how do you find x of 1 minus 3t? Is they all the three effects are combined. So you observe that there is a time scaling is there, so amplitude shift is there, reversal is there. So you observe that there are many effects involved in this particular fourth case, that is D. So you apply the same t dash, take t dash as 1 minus 3t, and you observe this case, you are going to get t lying between 1 by 3 and as well as minus 2 by 3, and just plot that. So we got x of 1 minus 3t plot. So this is how you can easily easily plot x of 1 minus 3t. And now there is another classification of signals. This is important again, even and odd, especially when we deal with our Fourier series and other topics. We are going to make use of the some of the topics which we have discussed. So these are very important for us. A continuous function x is given, and x of t is given. Say for example, continuous function x of t is given to us, and you are asked to find out whether the given x of t is even or not. Then what you have to do is you have to check for the condition of x of minus t for all t. And if you get x of minus t same as x of t, you can say that it is an even one. And the same can be applied for discrete functions also. Observe that continuous time function is represented with x of t, whereas discrete function is represented with the x of n. And you got x of n as if you find x of minus n same as x of n, then you can say that the discrete function is a even function. So geometrically, how do you say about the even signal is a symmetric about the origin. So you take the origin here. On both sides of the origin, you will find, that means on the left hand side and as well as right hand side, you will find the signal as symmetric. So that is what the meaning of symmetric. So here you observe this is the case of a continuous function, whereas this is the case of a discrete function. On the right hand side, you have the case of a discrete function where you have x of n value defined at n is equal to 1 and n is equal to 2 and n is equal to 3. Yet x of n at n is equal to 1 is having an amplitude -2. And here also you observe x of minus n is also having, that is x of minus 1 is also having an amplitude of -2. Similarly, you observe x of 2 is having amplitude 2 and x of -2 also has the amplitude 2. So it is symmetric in nature, and so on. It is symmetric in nature. Now, classification, even signals, these are symmetrical or mirror images about y-axis. Let us take multiple examples for this. So this is the case of, you observe on both sides you have a symmetric about y-axis. The signal is being symmetric. Here on left hand side you have -1, and again here on the right hand side +1 on the time axis, and the second signal is also symmetric, and the third signal is again a symmetric one. You take on the about the origin and observe the signal on both sides of the origin, so it is the same. So hence it can be said as symmetric. Another way of finding, suppose you are given an equation x of t is equal to cos omega naught t, and you are asked to find out whether it is a even signal or an odd signal, then just substitute t is equal to -t, and hence one can find out x of -t as cos of omega naught multiplied with -t, cos of minus omega naught t, cos of a negative value is a cos omega naught t, cos of minus theta is cos theta, and hence here in this case x of minus t became x of t. And classification of signals in this, again, odd signal. So far we discussed about the even signal. Now we will see what is an odd signal quickly. So x of minus t you find, and then minus of x of minus t, then it becomes an odd signal. A function s is said to be odd if it satisfies, in the case of a discrete signal x of n, it can be said as an odd function if minus x of minus n is same as x of n. And as in the case of even signal, it is symmetric. It is the opposite here. Geometrically, the graph of an odd signal is anti-symmetric about the origin. So you take an example here. You are not going to have the same amplitude at these time instants on the left side and as well as on the right side. They are going to vary. So this is one example. Okay, and here again you observe here at n is equal to 1, it is a discrete. N is equal to 1, it is having an amplitude 1, whereas at n is equal to 2, it is having an amplitude of 2. When it comes here at n is equal to -1, it is having an amplitude of -1. So x of minus n is not same as x of x of minus n, again minus of x of minus n, okay, is the same. Hence we are going to have it as an odd signal. So you take here just this case, x of -1 is -1, and that is to be multiplied with -1. So -1 multiplied with -1, it becomes +1. So it is same as x of +1, which is having an amplitude of 1. Hence you can confirm this discrete sequence or signal as an odd, as it is satisfying the condition of minus x of minus n, which is same as x of n. So this is the case of odd signal. So odd signal, these are again, here is a mistake. There are anti-symmetrical or mirror image about y-axis. X of minus t as minus x of t, or x of t is equal to minus x of minus t. These are anti-symmetrical, not symmetrical. Symmetrical or even signal, anti-symmetrical or odd signal. So you observe. So you take x of t and you do the time reversal, and then you do the amplitude reversal. So the if you perform two operations, that is time reversal operation and amplitude reversal operation on a single signal, you are going to get an odd signal, right? So this is how you can understand to obtain an odd signal, just you perform time reversal operation and as well as amplitude reversal, so that you are able to get minus x of minus t. So that is the case of an odd signal. And x of t is given as sine omega naught t, and you are asked to find out whether it is an even signal or odd signal. You substitute minus t, sine of omega naught of minus t, sine of minus theta is equal to theta. So we got minus sine omega naught t. So it is minus x of t, hence it is an odd signal. The average value of an odd signal is 0, but the converse of this statement is not true. This is an important note that one has to understand. Now, if you are given a signal, the signal can be decomposed into an even component and odd component. So here we can try to get the even component and odd component of a given signal. So if f of t is given, that can be written in the form of 1 by 2 f of t plus f of minus t plus 1 by 2 f of t minus of f of minus t. So this is the equation, and the even component is the average of these two, and the odd component is f of from f of t. F of minus t is subtracted, and it is divided by 2. So we got the combination of even component and odd component. And any signal, you can divide it into even and odd, and it can be represented as x even, x of t plus x of minus t by 2. And similarly, odd component is this. So the important properties of even and odd function, these are especially useful in solving the problems very quickly. Suppose you are given a big equation with a number of terms, and you are asked to find out the even part and odd part of it. Just you can quickly find which is the even part function and the odd part function. So for suppose an even function is multiplied with an odd function, the resultant is an odd function. If you multiply two odd functions, the resultant will be even function, and the multiplication of two even functions will result in an even function. And here we can find the area. Suppose the limits are minus a to a, fe of t dt is there. It is same as 2 integral. You observe the lower limit being changed to 0 to a, fe of t dt. So you can find minus a to a integral fe of t dt as same area under that one. So just whatever the important point we have seen was kept here in the form of the time equations. Suppose we have t square and t power 4, just to show that multiplication of two even functions will result in an even function. You observe that t power 6 is even. So you multiply even with odd, you observe that we got t power 5. So 5 here, the exponent value is an odd. You again multiply odd and odd, you are going to get even. So you t cube and t power 5, it is resulting in an even value, even function. Sorry. So here again, division by odd function by an odd function is going to result as even. Similarly, summation of two even functions results in an even, and subtraction of two even functions will result in an even function, and addition of two odd functions will result in an odd function. You observe here sine of t. What is sine of t? Is an odd. Just now we substituted t is equal to minus t. In place of t, we can substitute minus t. Sine of minus t is minus sine t. So hence it is odd function. So in place of t, you substitute minus t whole cube will result in minus t cube, and hence both the odd function added with odd function, the result is an odd function. And again, you take an even function and add it to an odd function, you are going to get neither even nor odd function. So this is the case. So you observe x of t, which is t square plus sine t, and x of minus t is t square minus sine t. You observe that both x of t and x of minus t are unrelated. Either it is x of t is not equal to x of minus t, or minus x of minus t is not equal to x of t. So hence, this is neither even nor odd case. And now you are given a problem, say simply a direct current signal x of t is having a constant amplitude, x of t is equal to 2, and now replace t with minus t. You observe that the equation is independent of time t, and hence x of minus t is same as x of t. Clearly it is the case of an even signal. Now, take another example. X of t is sine t square. You observe that it is not sine of t, sine of t square. So you need to substitute in place of t minus t. So if you substitute minus t, sine of minus t whole square, that will result in sine of t square. So as sine of t square is same as x of t, x of minus t is same as x of t. It is a clear case of an even signal. Now, you are given x of t is equal to sine pi by 2. Okay, and it is again, you observe that the equation is independent of time period. So it is like the case of a DC signal, and x of minus t is sine pi by 2, which is equal to 1, and DC signal is an even signal. Now, this is what I am talking about. Suppose you are given a big signal having multiple number of terms, and you are asked to quickly identify the even and odd part of that particular signal. Then whatever the operations, just now we discussed that division of an even by an odd, division of an even signal by an even signal, multiplication of odd signals. So quickly we can find out whether it is an even or an odd part. So for example, 3 is a DC, it is an even, independent of time period. Upper one is an even, t square is an even. If you substitute t is equal to minus t whole square is same as t square, so it is even. Sine of minus t is minus sine t, it is odd. And you take the third term. What is the third term? Third term is cos of t divided by t. Substitute t is equal to minus t. So cos of minus t is minus cos. Cos of minus t is plus cos t only. Cos of minus theta is cos theta only. So it is an even. And then substitute t as minus t. So it is an odd. And minus sine square of t, it is even. Even again divided by even, we got it as even, and odd multiplied with odd, we got it again an even signal. And x of an even signal, so from x of t you just get the even part as 3 minus sine square t by t power 4 plus t cube sine cube t. So we have just segregated the even terms and written the even part here. The first one is even, and from the extreme left hand side I'm talking about, the fourth one is even, and again the fifth one is even. Just write those terms so that we will get the even part of the given signal. Similarly, odd part, how do we get is the second term is an odd, and the third one is also an odd. Just write minus t square by sine t plus cos t by t. So we got the odd portion of this particular signal. So we can easily find even and odd signals, odd parts of a given signal, just by making use of these simple properties. That is the one. Now, let us take an important question here. For each of the following signals, you are asked to find even, odd, or neither even nor odd. Neither even nor odd. Just take just a few seconds, because by this time one can easily, the way that we had done number of examples on this, one can easily identify within no time the answers for this one. So if you observe the first case, it is a symmetric one, right? X of minus t is same as, it is symmetric about your y-axis. So you can easily identify that. And now take the second case. So the first case, by definition, the signal is even if and only if x of minus t is same as x of t. And since x of t is symmetric about t is equal to 0, it is the even case. Now take the second one, second example, that is B, you observe in this particular case, x of minus t, just you try to find out x of minus t. So how do I get x of minus t is mirror image of this, and then you try to find out minus of x of t. So in both cases, you are not going to get either x of minus t is same as x of t, or minus of x of minus t is also yeah is also not equal to x of t. So the case B is a clear case of neither even nor odd. And you go to the figure C, and this is x of t, and which is having, okay, the amplitude here as 1 at t is equal to 1, right? And here at t is equal to minus 1, it has an amplitude of minus 1. And this is the figure C. Now try to quickly identify whether it is an even signal or an odd signal. So I think you got it. Just I'm going to explain you. It is the case of an odd signal, because minus x of minus t, you try to identify. How do we get my x of minus t is the mirror image of this, and then just do the amplitude reversal. So it is a clear case of odd signal. So we have time reversal and amplitude reversal combined is going to result in the same original signal. We can identify that the given signal is a clear odd signal. So that is the important concept that one has to identify. And the fourth diagram is a little bit tricky. You observe that on the left hand side, it is a discretized one. The amplitudes are going to start from n is equal to minus 1. Whereas yet n is equal to 0 itself, here you got an amplitude of 1. See, if you suddenly see this one, you may mistake this as the case of as there exists an amplitude even at n is equal to 1. It is going to start at n is equal to 1. No, it's not going to start from n is equal to 1. You clearly observe it is going to start from n is equal to 0. So that's where the students generally in a hurry will, in a hasty manner, will make a mistake. So you have to be very keen in observing where the amplitude is going to start. So that's the reason why this kind of questions are chosen, so that you may not make the mistake and you thoroughly identify. Here x of n seems like an odd signal at first glance, because you may think that the amplitudes are going to start from n is equal to 1 onwards, but unfortunately it is going to start at n is equal to 0. So at first, however, note that x of n is minus of x of minus n. Evaluated at n is equal to 0 implies x of 0 should be same as minus x of 0. But the minus x of 0 is not existent. Okay, x of 0 should, x of minus 0 is, there is no. Yeah, so here you observe that x of 0 minus x of 0 or x of 0 is equal to 0. The analogous result applies to continuous time signal. The signal is therefore neither the case of even nor an odd. So this is the one. So we have taken all the different kinds of problems, and we had tried to apply the concept of the even and odd signal identification on these problems. Now again, another example problem for the case of even and odd. Yeah, so how do you get an even part? Just now we discussed, we have to take the average of the signal x of, that is x of t, x of minus t by 2. So you get the even, and odd part is half of x of minus t minus x of minus t. So these are plotted here very clearly. So you take x of t first, do the time reversal. How do you do the time reversal? How do you get this in an easy manner? Is just the mirror image of this is x of minus t. Then you take the average of, so we are now aware of x of t signal and x of minus t signal. So if I add x of t and x of minus t at a time instant of minus 1, is there any amplitude for x of t? I have to observe. And yeah, so that's why you got here. Yet t is equal to 0, the amplitude is 2 here, and here also the amplitude 2. So here in the average, so I got here 2. And then, yeah, then what? So here at t is equal to 1, okay, in the x of minus t case, and x of t case at t is equal to 1, this is the amplitude. As a result, you got this. And now subtracting x of minus t from x of t is going to result in this waveform. So this is the case. Now, another important classification is like whether the given signal is a periodic signal or a periodic or a non-periodic signal. So you may be asked to find whether the given signal is a periodic signal or a non-periodic signal. So for that, what is required for us is the definition of a periodic signal. So we try to learn what is a function x is said to be periodic with periodicity if some positive real constant t is taken, and if you get the satisfactory relation of x of t plus t as same as x of t for all t, then you can say that signal as a periodic signal. A t periodic function x is said to have frequency 1 by t and angular frequency 2 pi by t, and a sequence x is said to be periodic with period n for some strictly positive integer constant n. The following condition that holds: x of n plus n same as x of n. So you observe the two conditions. One is the case of continuous time, another is the case of a discrete sequence. So x of n same as x of n plus n is the case of a discrete one, and x of t same as x of t plus t is the case of a continuous time. So an n periodic sequence x is said to have a frequency. In that case, for that particular discrete signal you or sequence, you have a frequency of 1 by n, and the angular frequency is given by 2 pi by n. Whereas here, in place of n, for the periodic function which is continuous in time, you will get a 2 pi by t. So a function or a sequence that is not periodic is said to be aperiodic. So we will use often the terms periodic, non-periodic, or aperiodic. Some examples of periodic signals are shown here. So these are the examples of the periodic signal. So you do x of t plus t, you observe that x of t plus t is same as x of t, and this is the case of a discrete sequence. Here also you observe x of small n plus capital N same as x of n. That is the case of a periodic discrete sequence. Now, you are having a simple periodic function. A signal repeats itself after some time period. The signal is said to be periodic. So we can have a multiplication by an integer, added or subtracted. So x of t is equal to x of t plus or minus n t naught, where n is an integer and the t naught is a fundamental time period. So this fundamental time period is very important, and in most of the problems you may be asked to find the fundamental time period of a given sequence, or it may be useful as an internal problem in a big problem, so that one has to find the fundamental time period of a given signal. So then you will find the use of this concept. It is the smallest positive integer and fixed value. Which one? For the fundamental time period is the smallest positive and fixed value of time for which the signal is periodic. So find the fundamental time period of a given signal. You are given a signal with these intervals 0 to 1 and 1 to 2, and t naught is given as 1. And now you try to find out the fundamental time period. You observe that the fundamental time period is 1, and it is getting it is the smallest integer, positive integer. So you take the case of a generalized equation, calculate the fundamental time period of a signal. We will take a signal x of t, a naught e power j omega naught t. So let t naught be the fundamental time period of the signal, and just we are trying to find out the equation for the fundamental time period by this exercise, simple exercise. X of, so as per the definition of this, x of t plus t naught, periodic signal. For a periodic signal, x of t plus t naught is same as x of t. So whereas here you observe, in place of n we have 1, that is the smallest possible positive integer. N is equal to 1, we substituted, so that on the right hand side we got x of t plus t naught. X of t plus t naught is equal to a naught e power j omega naught t plus t naught. And now on the left hand side, as you are aware of, x of t is equal to x of t plus t naught. Just let us substitute that. In place of x of t, I am going to substitute a naught e power j omega naught t, and on the right hand side, wherever t is there, I have to replace it with t plus t naught. So I am replacing t with t plus t naught, a naught e power j omega naught, and here t plus t naught. So we got e power j omega naught t plus t naught. So this is of the form e power j a plus b. So or e power j x plus y. So if the base are the same, the exponential terms can be added. So what you can do is e power jx, j of x plus y is there, which can be done as e power jx multiplied with e power jy. Just separate those two exponential terms. So you observe, if I separate them, a naught e power j omega naught t here, and e power j omega naught t naught. So you observe here on both sides, we have a naught e power j omega naught t term is there, both gets cancelled, and we are left with e power j omega naught t naught, and that is equal to 1. And yeah, if you substitute the smallest possible value, this is taken as e power j 2 pi k, and the smallest possible value of k or n is 1. So if you substitute 2 pi k by omega naught and take k as 1, as it is the smallest possible positive integer, as a result, we had shown the fundamental time period for a signal given by a naught e power j omega naught t as t naught is equal to 2 pi by omega naught. And we can make use of this particular result everywhere in many problems. For example, here are 3 problems based on this simple concept. You are given x1 of t as a naught sine 2 pi t, and as per the derivation just we did, the fundamental time period t naught is equal to 2 pi by omega naught, and it is of the form a naught sine omega naught t. In place of omega naught, we have 2 pi. So we substitute in place of omega naught the value of 2 pi, and hence we got the fundamental time period as 1 here. And now take the second case, a naught sine 2 pi t plus 30 degrees. So it is the case of a naught sine omega naught t plus some phase angle 30 degrees. So irrespective of that, our fundamental time period is just dependent on the omega naught value. So t naught is given by t naught is equal to 2 pi by omega naught. And in place of omega naught, just substitute 2 pi. So 2 pi divided by 2 pi, we got it as 1. So we got the fundamental time period for x2 of t, which is a naught sine 2 pi t plus 30 as 1. And similarly, x3 of t, which is minus x1 of t, and you find the fundamental time period as 1. So what you can observe is, if a signal, a periodic signal, is either time shifted or it is amplitude scaled, the fundamental time period is not going to change. And we can make that conclusion by taking a few more examples, like x4 of t is equal to x1 of minus t. See, why this discussion is, if you just readily, if you keep the important point in mind that the fundamental time period is not going to change either by time scaling, time shifting, for this particular case. So then you can easily solve the objective type questions. That's where you can save a lot of time. So that's why you have to understand these this important concept. So x1 of minus t a naught sine 2 pi minus of t minus a naught sine 2 pi t, and you can find the fundamental time period as 1. Here in this case also, you can find the fundamental time period a naught plus x1 of t. What is this? This is the case of a simple amplitude shift case. So you observe again, we got the fundamental time period as 1. So for all the 5 cases, you got the fundamental time period as 1, and x6 of t, which is x1 of t minus t naught, and again a naught sine 2 pi t minus t naught. As per the equation, t naught is equal to 2 pi by omega naught, and we got 1. So an important note that one can observe is, time period of the signal is unaffected by time shifting, time reversal, fundamental time period. Okay, here it should be like fundamental time period is unaffected with time shifting, time reversal, amplitude shifting, and change in phase of the signal. These are not going to affect the fundamental time period of a signal. This is what an important conclusion that we have drawn by discussing these 6 different examples. Now, let us take this case. Sine square 4 pi t. See, we are aware of, this is not of the form a naught sine omega naught t, a naught sine omega naught t, because there for the sine there is no square term that for the fundamental time period equation derivation which we have taken. So there is a need for conversion of that squared sine term, making use of its equivalent. Like, that's the reason why you observe that the sine square theta is converted as 1 minus cos 2 theta by 2, where theta is here in this case is 4 pi t. So 1 minus cos 2 theta is, theta being 4 pi t, 2 theta will become 8 pi t. So 1 minus cos 8 pi t divided by 2. So we will get the fundamental time period very easily by, now we can easily observe cos omega naught t. This is a standard case again. So cos omega naught t, and omega naught one can directly identify it as 8 pi, and t naught is equal to 2 pi by omega naught, and omega naught is 8 pi, so that we will get t naught, the fundamental time period, as 1 by 4. So this is another case. And often it is useful, like you have number of periodic functions added in a big equation, and there are number of periodic functions. See, and you may be asked to find the fundamental time period of this big sum of periodic functions. Number of periodic functions are there in a equation, and you may be given a simple objective question, and you need to find that very quickly. Then here is a tip or a trick and a simple solution that one can easily do. So let us try to concentrate on this one, as this is very important. We have x1 and x2 periodic functions with period t1 and t2. Then whether the sum of these two periodic functions is a periodic function or not. How do we identify is that we take the ratio of the time periods of these periodic functions, okay, and then we will observe that whether the ratio is a rational number or not. Suppose that t1 by t2 is equal to q by r, where q and r are integers, and co-prime. What is meant by co-prime is they do not have any common factor. Then the fundamental time period y is said to be rt of rt1, and or equivalent qt2, since rt1 is equal to qt2. This you better understand by taking a numerical example. You will appreciate it, and you can easily understand how to find the fundamental time period of the given two sum of periodic functions. So although above theorem only directly addresses the case of sum of two functions, the case of n functions can be handled applying this theorem repeatedly n minus 1 times. So though you take it for, here we discussed for the case of t1 by 2 t2, but you can, yeah, you can repeat this for number of functions, n number of functions. So we are asked to find the fundamental time period of sum of two or more signals. Sum of two or more signals. We are asked to find. So x of t is equal to x1 of t plus x2 of t. This is given. Then if x1 of t is having a time period of t1 and frequency f1, and omega 1 is the angular frequency. See, one need to identify the difference between f1 and omega 1. F1 is called linear frequency, whereas omega 1 is called angular frequency. And yeah, for for this one you are given the ratio. You need to find out the ratio, the relation between the angular frequency and the linear frequency. Omega is the angular frequency and f is the linear frequency. Omega is equal to 2 pi f, right? And you take the ratios, either any of the ratios like t1 by t2 ratio, or angular frequency ratios like omega 1 by omega 2, or the ratio of f1 by f2. They must be rational. So you can find the fundamental time period by having the simple concept of take the least common multiplier, which is t1 comma t2, or f naught. If we are finding out the frequency, in that case it is the highest common factor. You observe, if I am finding time period, it is I need to take the LCM, least common multiplier, and it becomes reverse for fundamental frequency. Like here I have taken least common multiplier, whereas here I have to take the case of highest common factor of f1 comma f2. And now we will try to find out the fundamental time period of a given signal by taking an example. The example given is x of t is equal to sine 2t cos 3 pi t. Now it is of the form a naught sine omega naught plus a naught cos omega naught t. And one can observe omega 1 for the first one as a 2, and omega 2, that is for the second function as periodic function, say it is cos 3 pi t. So your omega 2 becomes 3 pi. Now take the ratio of these two angular frequencies. The first angular frequency is 2 and the second angular frequency is 3 pi. So 2 by 3 pi, is it rational or irrational? So it is irrational. Why irrational? So we are not getting a ratio of integers, like numerator is integer, fine, but denominator, is it integer? No, it is not integer. 3 into pi is 3.1415. So if you multiply 3 with 1415, we are not going to get an integer value in the denominator. So hence it is a non-periodic, as the ratio of omega 1 by omega 2 is irrational. So clearly we can find out, and one may say it is a non-periodic function. Now take the second case, and sin 2 pi t is given, cos of root 2 pi t is given. We can observe that for the first one, the omega 1 value is 2 pi, as sine of omega 1 t plus cos of omega 2 t. In place of omega 1 we have 2 pi, in place of omega 2 we have root 2 pi. So now take the ratio 2 pi divided by root 2 pi. So we are going to get a value of root 2, which is 1.414, and it is clearly a case of a irrational number. Hence it is non-periodic in nature. So this particular examples, if we get the ratio of either angular frequencies or time periods as a rational number, both numerator and denominators are integer in nature, it is a clear case of a rational number, and the signal is said to be periodic. Whereas now in both these cases, we got the result as irrational, and here it is the case of a non-periodic signal. And we will take example problems on FTP, on the fundamental time period. Again, we are given a sine 4 pi t and sine 7 pi t. And now compute the ratio 4 pi by 7 pi. 4 by 7, it is a rational number, hence it is periodic in nature, and we can calculate the fundamental time period very easily. And you can have two methods, okay, either by taking the least common factors or the highest common factors. Whichever you feel very comfortable, you can adopt, and whichever you feel very quickly that you can do or confidently, adopt that method and proceed in that manner. As we discussed, highest common factor of the two angular frequencies. What are the equations given? Sine 4 pi t plus sine 7 pi t, and highest common factor of 4 pi comma 7 pi is omega naught. So here we get highest common factor of 4 pi comma 7 pi as pi. Am I right? What is the highest common factor of 4 pi comma 7 pi? There is a common factor of pi, and you will take that as omega naught and compute the fundamental time period, which is given by t naught is equal to 2 pi by omega naught. In place of omega naught, substitute pi, so that you will get 2. This is the first method. And let us take the second method, in which we are computing the independent time periods for the first signal. 2 pi by omega 1 is the time period, and for the first signal it is sine 4 pi t. The omega 1 value is 4 pi. 2 pi by 4 pi, it is 1 by 2. We got p1 by q1, p1 being 1, q1 being 2. And again, for the t2, it is not t1 again, 2 pi by omega 2, it is 2 pi by 7 pi, and as a result we got 2 by 7. Now take the least common factor of t1 comma t2. The first one is 1 by 2, least common factor of 1 by 2 comma 2 by 7. So or that is LCM of 1 comma 2 divided by highest common factor of 2 comma 7. So least common multiplier is 2. The numerator we got it 2. Highest common factor between for 2 and 7 is 1. We got the period as 2. So you can observe that rather doing it with method 1 is very easy, like, because in the second method you have to apply both the concept of LCM and as well as highest common factor. So a little bit time consuming for the second method. Whereas in the first method, you can easily find the fundamental time period. Okay, so that this is where you can save some time and quickly do such objective type question, multiple choice questions in an easier and efficient manner. Now, the next important concept is you will be given a signal and you will be asked to find the energy and the power of the signal. The energy E contained in the signal X is given by E is equal to integral minus infinity to infinity X of t whole square dt. This is the fundamental equation for finding the energy of a given signal. A signal with finite energy is said to be energy signal. So the condition is that the value should be a finite. Okay, which value? The energy value is a finite value. The average power contained in the signal can be computed making use of energy of the signal. So you observe limit t tends to infinity 1 by time period over the period minus t by 2 to x of t whole square dt is going to give us the average power. A signal with finite average power is said to be a power signal. And you can see the equations here. From these equations, we are going to deduce a simple one. Energy of the signal are absolutely integrable, or it should be finite in nature. That is the reason why here you will find an important condition. Integral minus infinity to infinity x of t dt should be less than infinity. So here the square root term x of t is equal to mod of x of t is given by integral minus infinity to infinity x of mod of x of t whole square dt. That is the energy of a given signal. Energy of x of t is equal to integral minus infinity to infinity mod of x of t whole square dt, so that one can find out the energy of a signal. How do we get the power? Is limit t naught tends to infinity integral minus t naught by 2 to t naught by 2 x of t whole square dt. This is the case of a non-periodic signal. So the finding the power, there are two cases. One is the case of a periodic signal, another is the case of a non-periodic signal. So the equation for periodic signal is given by this one, 1 by t naught integral minus t naught by 2 to t naught by 2 mod of x of t whole square dt. And the energy of the signal is absolutely integrable. And you just will take a problem and try to solve this problem. X of t is e power minus t 2t and u of t. And actually, this concept of u of t, we are going to discuss about this u of t signal. But for time being, let us try to understand for all t greater than or equal to 0, your u of t can be replaced by 1. So that is what the property of u of t. We'll discuss in detail about different types of signals like your the impulse signal, your step signal, ramp signal, that we are going to discuss. So for time being, for here we limit our case to find the energy of a signal, and you just for this particular problem we try to say u of t is 1 for t greater than or equal to 0. So it is therefore minus t integral minus t to t x of t whole square dt, and that can be taken as integral 0 to t. Why the integral was the limits are changed? You observe that it is e power minus 2t only for t greater than or equal to 0. So you have taken the limits as here integral 0 to t. That means you have between the time integrand minus t to 0, it is 0. So here you have to substitute your x of t as e power minus 2t, that is modulus of e power minus 2t whole square dt. That is what the definition. So you have to compute this integrand. Okay, so the student should be thorough with the integration and as well as differentiation. Integral of e power minus 2t whole square, it is e power minus 4t. Integral by e power minus 4t dt is equal to, it is of the form e power at dt, integral e power at dt is equal to e power at divided by a, where a is the scaling factor. In case of a, here we have -4, just substitute that. So that e power minus 4t by minus 4, apply the upper limit as t, capital T, and apply the lower limit as 0. So if you substitute e power 0 as 1, and yeah, here minus 4. So we got e power minus 4t, e power 0 is 1. So which is 1 by 4 minus e power minus 4t by 4 as the value of this integrand. And energy of this is limit t tends to infinity, minus t to t x of mod of x of t whole square dt, and that is given by this one. So 1 by 4 will apply the limit as limit t tends to infinity, and what happens is e power minus infinity. What is the value of e power minus infinity is 1 by e power infinity. It can be taken as 1 by e power infinity, as e power minus infinity is 1 by e power infinity. 1 by infinity value, it will result in a this zero value. So 0 by 4. So we got 1 by 4 joules as joules are the units for this energy, and power of the signal can be computed making use of limit t tends to infinity 1 by 2t integral minus t to t x of t whole square dt, and the power can be computed this. So as we have seen, it is to be understood that whether the signal is a periodic signal or a non-periodic signal, accordingly the equation is to be applied. Since energy is constant and power is 0, the given signal is an energy signal, because we computed the value of power as 0, and hence one can conclude this signal as a energy signal rather than the power signal, because power doesn't exist, power is 0, and we are asked to find the energy. So now we are going to see a simple case. Instead of doing the integration and computing these values, the energy of a signal can be find easily. The area of with a simple concept of area of mod of x of t whole square. So you take the case of energy E is given by E is equal to integral minus infinity to infinity mod of x of t whole square dt, and as mod of x of t, you observe it as the case of this, the amplitude is being 4 square dt. So as a result, 4 square is 16 dt. Substitute the upper limit as 2, 16 into 2 minus 16 into 0. You got 32 joules as the energy of this signal. Or in a simpler manner, area of mod of x of t whole square. So this is whole square of this 4 square is 16, and you have on the width side, on the width side, you have on the time period scale, here you will find it as 2, between 0 and 2. Just multiply with that. So you are going to get the area under this one as 16 into 2 as 32. Similarly, you take the other examples. Here is the case where you have a signal in between 0 to 1, the amplitude is plus 2, and in between the time limits of 1 and 2, plus 1 and plus 2, the amplitude is being minus 2, and between 0 and minus 1, the amplitude as minus 2. Now, how do, from x of t, x square of t can be obtained very easily. Square of this minus 2, mod of minus 2 whole square will result in a value of 4. That is the reason why when I am plotting this graph, yet in between minus 1 and 0, the amplitude was plotted on the even on the negative side as 4, because minus mod of minus 2 whole square as 4. And similarly here plus 2 is the amplitude in between 0 and 1. In between 0 and 1, plus 2 whole square That resulted in an amplitude of 4. Similarly, here amplitude is -2 whole square, again 4. So you got this amplitude as 4, and it is getting extended from between the time limits of -1 to +2, and you can find the energy of this signal as this, and area of this is already x square we have computed, which is 4, and 2 minus of -1. What is the 2 minus of -1 is 3. So hence the area of mod of x of t whole square is 12. So we got the energy of the signal in an easier manner. Similarly, we are given another signal. Suppose you are given this plot, and you observe that this is like y is equal to mx form. And how do you find the slope of that plot is, as you know, m is equal to slope is, you have the coordinates, suppose 2 points, x1 y1, x2 y2. How do I find the slope? As slope is equal to y2 minus y1 by x2 minus x1. So in this case, the value of y2 is 2 and y1 is being 0. 2 minus 0 divided by x2 being 1 and x1 being origin O00. So x1 by 1 are 0 0, and y2 and y2 value is your amplitude on this one, right? X of t, and this is x-axis and this is y-axis. You can observe this is the signal x of t. So you can observe, so 2 minus 0 divided by 1 minus 0, which is 2. So we got the equation as x of t is equal to simply 2t. So as per the definition of energy of a signal, it is 2t square dt, and 4 by 3. Here we can easily find by this equation. So though we are not given the x of t equation, one can easily find x of t by the plot, making use of its shape and the form. One can easily write the equation. Now, x of t signal has energy E. Find the energy of the signal x of 2t. So how do you find is, apply the same concept. E is the area of x of t whole square, which is equal to 4 x of 2t, area of x of 2t whole square. And you can observe that, yeah, now you observe x of t signal is known to us. How do I find x of 2t? Here you apply the concept of time scale. So multiplication by a factor, scaling factor of a greater than 1 will compress the signal. So after compressing, you observe the time limits are 0 to 0.5 rather than 0 to 1. These are for x of t, these time limits, and these time limits are for x of 2t, and hence the area of mod of x of 2t whole square is amplitude square, that is 2 square, into this particular on the time axis 0.5, 0 in between 0 and 0.5. So one can easily find the energy of this as 2. So for a time scaled signal, the energy is going to decrease. Okay, so important point to remember. So for a x of t, for a given x of t signal, if the energy is E, for x of 2t, it is E by 2 for a time scaled one. For a time scaled and time reversed also, it is E by 2. The reason is being like we are taking modulus. So x of at is given in a generalized case, where a is the scaling factor. We are going to get E by mod of a as the energy of a time scaled signal by a scaling factor of a. Energy of a signal is independent of. So what is the conclusion? See, by all these examples, we have drawn a very important point. What is that very important point is energy of a signal is independent of amplitude reversal, time reversal, comma, time shifting. For all these signals, you observe that the energy is being the same as 4. So this is the given original x of t signal, and x of t is time shifted by 1 unit, x of t minus 1. X of t is time reversed. For that also we got energy value as 4. Okay, and as well as here we have got amplitude reversal. How amplitude reversal is x of t is multiplied with minus 1, so that we got minus x of t. So though we perform the operations of amplitude reversal, time shifting, we can observe that the energy of the signal is independent of amplitude reversal, time reversal, and as well as time shifting. We can clearly understand that. And now, coming to this power signal. For the signal, power should be finite and energy should be infinite. The periodic power signal are absolutely integrable over their time period. The important point is periodic power signals are absolutely integrable over their time period. So that is integral mod of x of t dt should be less than infinity. That is a periodic power signal. And for periodic power signal, we have repeated these equations. We have already discussed this. Again, for our convenience, we repeated the equations for power for periodic and as well as for non-periodic signal, as we are going to compute, and we are summarizing here and making use of this concept again for computing the power of a given signal. So find the power of a pulse signal. We are given this waveform, and this is a pulse signal, and it is having some amplitude A naught. Amplitude A naught is clearly given here, and on the x-axis between 0 to t naught by 2, the amplitude is A naught, and in between t naught by 2 to t naught, there is 0 amplitude. Again, in between t naught, okay, to next t naught by 2, that means t naught plus t naught by 2, it is again a naught, the amplitude. Again, between minus t naught by 2 to minus t naught, the amplitude is a naught. And now the power equation is, this equation is to be applied. Now there are two equations. Clearly we can understand the given waveform or the given signal is periodic in nature. So we need to apply this equation for power computation rather than limit t naught tends to infinity 1 by t naught. This is for the case of a non-periodic signal, but we can observe that this is periodic in nature, and hence we have to apply the equation for power computation for a periodic case. So for a periodic case, the power signal is given by P is equal to 1 by T naught, integral minus T naught by 2 to T naught by 2, mod of x of t whole square dt, and we have to substitute the amplitude of the signal as A naught, and yeah, so in between this, the amplitude is a naught square. So you observe it can be taken as a naught square by t naught, and in between integral 0 to t naught by 2, it is simply integral dt is t, which is t naught by 2. We got the power as a naught square by 2. Power is also known as mean square value of the signal. Mean square value of the signal. It is also mean square. Find the power of a triangular waveform. So as you observe, the triangular waveform is having an amplitude of again a naught, and it is having the peak at t naught by 2, and the start time period for the first triangular waveform at t is equal to 0, and the other one at t is equal to t naught is the amplitude is again becoming 0. Again, the amplitude is becoming a naught here, that is 3t naught by 2, plus again t naught by 2, that is 2t naught. The amplitude is becoming 0. Now, just we have to find out the equation for x of t. How do we find is, it is of the form, just now we computed for a triangular waveform, the equation is, it is of the form y is equal to mx. The slope m can be found by the coordinates like y2 minus y1 divided by x2 minus x1. Here y2 being a naught and y1 being at the origin x1 y1 is 0 0, and we can find m, the slope, as a naught minus 0 divided by t naught by 2 minus 0. It is 2a naught by t naught, and we can find the power as 1 by t naught integral minus t naught by 2 to t naught by 2. And in place of x of t, we are going to substitute the equation for x of t as 2a naught by t naught whole square dt. 2a naught by t naught t, because x of t is equal to m into t. Okay, it is of the form y is equal to mx. In place of x, we have here t. So here t must be there. The slope m being 2a naught by t naught. So you can compute the value here, 2 by t naught integral 0 to t naught by 2. 2a naught by t naught whole square will result in 4a naught square by t naught square, and the small t whole square is t square dt. Now you observe this integral, we are doing the integration with respect to small t. So you can treat this 4a naught square by t naught square as a constant, and you can bring that outside the integral. As a result, 2 into 4a naught square, it is 8a naught square divided by t cube, and integral will get extended between the time limits 0 to t naught by 2, integral t square dt. So integral t square dt is t cube by 3, small t cube by 3. In place of small t, if I substitute the upper limit as capital T naught by 2, it is going to give me the result of t capital T naught cube by 8 minus 0. And as a result, I am going to get 8a naught square by t naught cube multiplied with t naught cube by 8, and it is going to give me the result as t naught by 2 whole square, t naught by 2 t cube by 3. So I am going to get t naught cube by 8 divided by 3. So in the denominator, there is a multiplication between 8 and 3, or I can cancel this 8 and 8. As a result, I got the power value for a triangular waveform as a naught square by 3, where a naught being the amplitude. Maybe in the exam, in place of a naught, I may have some amplitude, some numerical value. In that case, straight away I can compute the value. For example, a naught is equal to 2. So in that case, my power value, I can compute it as 2 square by 3, which may result in 4 by 3 units for the power. Okay, like watts or something like the units. So find the power of a given sinusoidal signal. So for a sinusoidal signal, the standard equation is given by a naught sine omega naught t is the standard equation for a given sinusoidal signal, and you are asked to find the power of that sinusoid. Clearly, a naught sine omega naught t is the case of a periodic signal. So one can find out the power for the given sinusoidal signal as in just we did the same exercise in the previous case also. It is x of t whole square dt mod of x of t whole square dt as sine square omega naught t can be computed taking 1 minus sine theta is equal to 1 minus cos 2 theta by 2. Just we will substitute here, and then 1 minus, in place of theta we have omega naught t, so you can substitute 1 minus cos 2 omega naught t dt, and 2a naught square by 2 t naught, and then we can compute this. You observe as we have here the denominator value as 2, and the limits are changed from instead of minus t naught by 2 to t naught by 2, it is changed to 0 to t naught by 2. We have a factor of 2 here. You observe that. So we got a naught square by t naught, and this is multiplied with the t naught by 2 minus sine 2 omega naught t divided by 2 omega naught, and the limits being 0 to t naught by 2, we can have the power of the signal as a naught square by 2. We know that the RMS value of a naught sine omega naught t as a naught by root 2, and the power is square of RMS value, and yeah, as a result, the this value a naught by root 2 whole square is resulting in a naught square by 2. That is what the power of a given sinusoidal signal can be computed, making use of a standard equation p is equal to 1 by t naught integral minus t naught by 2 t naught by 2 x of t whole square dt. This is a clear case of power calculation in the case of a given sinusoidal signal. And now we will take the previous gate questions based on the periodicity concept. In the gate 2013, we got a question. We are given a periodic signal v of t as 30 sine 100t plus 10 cos 300t plus 6 sine 500t plus pi by 4. So clearly this is the case of that multiple signals are there in the given equation, and the fundamental frequency is asked for us. Now, just by looking at the equation itself, we can compute the fundamental frequency as we had discussed earlier. We have in fact derived the simple equation and simple concept for finding the fundamental frequency of the given signal. So what is that we have understood from this particular one is, let us take the signal, and the signal is having various frequencies. For the first term, in the first term it is like sine omega 1t, and in the second term 10 cos omega 2t, and the third term is 6 sine omega 3t plus pi by 4, and you are asked to find the fundamental frequency of this. So let us take omega 1, which is 100 radians per second, omega 2, and for the angular frequency the units are radians per second. So 100 radians per second from the first term, from the second term 300 radians per second, and from the third term 500 radians per second. Therefore the respective time periods are, so how do I find time period? We know that f is 2 pi f is omega, and f is 1 by time period. Okay, relation between time period and linear frequency is inverse of time period is frequency, or inverse of frequency is time period, and we can find the time period by taking the ratio of 2 pi by omega 1. 2 pi by 100 seconds for the first term, as omega 1 is 100 and omega 2 is 300 here for the second term, hence we got 2 pi by 300, and omega 3 being 500, we got T3 as 2 pi by 500. So the fundamental time period of the signal is given by clearly the equation that we discussed earlier. We applied least common multiplier of all the numerator terms. This is of the form P1 by Q1, P2 by Q2, P3 by Q3, LCM of P1, comma P2, comma P3, and in all the three terms T1, T2, T3, P1, P2, P3 are the same, like 2 pi, 2 pi, 2 pi. And yeah, highest common factor of 100, 300, and 500. The common factor among all the three terms is the highest common factor being 100. We got 100 here, and the fundamental time period can be easily computed as T naught is equal to 2 pi by 100. Yeah, the explanation takes time, but you can do it instantly just making use of the concept of LCM of P1, P2, P3 divided by HCF of Q1, Q2, Q3. Just by looking at this, you need to identify this P1, P2, P3, Q1, Q2, Q3. If you remember, we have a detailed discussion. This T1 is a rational number, and the numerator being P1, denominator being Q1. And we can apply straight away that concept here, and within no time you can get the solution for the fundamental time period as 2 pi by this one. Okay, so that is hence the fundamental frequency. See, now you observe omega naught is equal to 2 pi f naught. Okay, and that is being this, you can find out omega naught is equal to 2 pi f naught, and 1 by time this one, so 100 radians per second. Okay, the power of a given signal. Compute the power of the given signal. Again, you are given one more problem. Again, cos of omega and sine of omega. And the first term being the cos term. 8 cos pi by 2 minus 20 pi t and 4 sine 15 pi t. This is what the given signal. And you can find the solution for this. Cos of pi by 2 minus theta being sine theta, 8 sine 20 pi t plus 4 sine 15 pi t, and A1 is the amplitude of the first one, which is being 8, and A2 is the amplitude of the second one, which is 4. Thus the power can be computed A1 square by 2 plus A2 square by 2. This we had derived in for the previous equations. For standard equations, we derived it as A0 square by 2. For the case of a sine function, A0 sine omega naught t, we derived the power equation as P is equal to A0 square by 2. Here we have two sine terms. One is with A1 sine omega 1t plus A2 sine omega 2t. And the power is given by A1 square by 2 plus A2 square by 2. A1 being 8, 8 square by 2 is 8, 64 by 2, 32 you are going to get, and 4 square by 2, that is 16 by 2, 8. As a result, you got the power as 40 units. And this is the GATE 2005 question. And yeah, what are given is option A 40, 41, 42, and 82. And we can clearly come to know that the computed value is 40. And yeah, the as the chat box facility is not there, all the students, if they are having any doubts regarding the problems or the concepts, they can fill the Google form, and they can mail it for the given mail, so that we can give the response in the next sessions by mentioning the question and the solution for that, in the same manner how we are explaining the solutions for the problems, and explaining the answers for the questions in a similar manner. If the students are having any questions or any doubts, we request all of you to fill the Google form and mail it back, so that the Google form will reach the subject person, and then the subject person in turn will respond to the questions of the students, and that will benefit the students. I thank all of you for taking much interest in this session, and thank you for this opportunity given from the authorities, from the university authorities of JNTU Kakinada and JNTU Anantapur, and AP State Council for Higher Education. If any queries are there, kindly send them. I once again thank for giving me this opportunity, and the material will be available for you to download from the website, which you can download later. Thank you.